For chapter 16, we're going to create a utility called FASTX grep. It's going to help us select sequences out of sequence files, which will include both FASTA and FASTQ, which is the reason for the FASTX. And the impetus for this was one time a friend had a set of FASTQ files and wanted me to extract all of the sequences that had the string LSU for long subunit RNA out of that FASTQ file. Now, I'm going to talk a little bit about the structure of FASTQ files to explain why you could actually solve this problem with just regular grep. But there are some subtle problems with that, and I'll explain this. And it just seemed like a good opportunity to write a program that could handle both FASTA and FASTQ, perhaps other file formats. And this program gets at much more of the kind of programs that I've written over my career, especially in Python. And so I thought it would be a good example. We could select records from sequence files based on other criteria like length or GC content. And it also gives us a chance to change the output format. So if we have FASTQ, which is often what you'll get from the sequencing center, and you actually want to output FASTA, which is generally what you need after you've done filtering and trimming, then maybe you need a utility to help you learn how to convert formats. So I'm here to show you that as well. So we're going to learn a bit about the structure of a FASTQ file. We have used regular expressions a few times now, but I haven't showed you how to do a case-insensitive search. I'm going to talk about the principles of DWIM, DWIM, do what I mean, and DRY, don't repeat yourself, in code. And we're going to also dig in a bit on and or operations, both logically and bitwise, to understand how to reduce Boolean values and bits, which I think is kind of cool. And a note here, grep is possibly short for global regular expression print. Not sure if we'll ever know the truth of that. So let's just talk real quick about how you could use the regular grep program, which will be kind of our model here. So if I grep for the string LSU in tests in this input file, and let's to get started, actually go to the top level of your directory of the GitHub checkout and do a source vnv bin activate. We're going to need to do this anyway. I always like to do it in a couple of windows. And then I'm going to go into the 16 FASTX grep directory, and then now we're all set up for what we're going to do later. Let's just use regular grep, which should be installed on your program, on your computer. And you'll see here mine finds two records, and it also highlights the string LSU here in a different color so that I can see where in the record it was found. So I found two lines that look like this, and they start with the @ sign, and that's going to be important. And if I'm just trying to find not the actual sequences themselves, but just how many I've found, I can pipe this output into the WC, which is the word count program. But I can tell it word count will actually count lines, characters, bytes, and words. And I'm telling it -L here because I only want it to count the lines of output. So if I were to run this same command, I should get the answer 2. So it finds 2 records. And our goal here is to do something kind of like this. I actually want to extract the records themselves. And so let's talk a little bit about the structure of a FASTQ format to understand why grep could actually do this all by itself. So the point of a FASTQ record, the point of a FASTQ file, is to get information about the quality of each one of the base calls. And there are many different ways of sequencing sequences, and depending on the kind of sequencer you're using, they're prone to certain kinds of errors. A common one is with homopolymer runs, so where you have many A's in a row, and as the number of A's grows, the confidence in each one of those bases being an A decreases, and so there's some math involved here, and the sequencer will output both the base call and some measure of certainty. And sometimes it's also hard to tell one base from another, which is why we get these IUPAC codes, such as R for either A or G, or N, which is just, it's unable to call any base with any confidence at all. So Ns are actually quite common to see. You might not necessarily see IUPAC codes. A lot of times what you'll want to do is to trim off the parts of the sequences that have low quality, such as the not very good confidence scores for the base calls, or you just simply want to get rid of Ns. Where you start seeing Ns pop up, you probably just have lost confidence in the rest of the sequence from that point forward. So FASTQ is similar to FASTA. They're not from the same people. So Bill Pearson created the FASTA format for the program FASTP and FASTA. FASTQ is kind of piggybacking on a already popular format and kind of giving something that is somewhat familiar to people. FASTA records start with a greater than sign, and FASTQ records are going to start with that @ sign that we saw. And so here I have the structure of a FASTQ record. And what you'll see here is that it starts with the @ sign. There is a sequence ID, just as in FASTA, and it is everything up to the first space, just as in FASTA. And then after that can be any sort of description, any sort of other metadata that whoever wants to put in there. After that has to be a single line of sequence. And this is going to be important because there's a third line that has just a plus sign. Sometimes it has a plus sign that's followed by all the data that's on the first line, which is really a terrible waste of space. And then there is a string of equal length to the sequence on the second line. The fourth line is of equal length, and it looks like gibberish. It looks like a bunch of punctuation and characters. But there is a one-to-one correspondence between this position, this base, and this character here. This character represents the quality of this position, the base call for that position. So what we can see here is that it looks like it's kind of in the character land here, and then it drops into some punctuation, and we're going to talk about what those mean. So this is in many ways a terrible file format. In the early days, they tried to split these up over multiple lines like a FASTA file, but the problem is this @ sign, you notice it also occurs in this line here. And as does we don't see an example here, but greater than signs could occur here too, because the punctuation could be the quality line. And so the problem is that, well, what if the very first base in the sequence has an @ sign for a quality? You would not be able to tell the beginning of an ID line from the beginning of a quality line. So it's really a terrible file format. Throw in this third line here, which serves no purpose whatsoever. It's just a plus sign. So we could easily just have 3 lines per record, but yeah, they didn't really think about this very well. So why are those characters what we're seeing on the quality line? Well, it has to do with the ASCII table. And in this directory here, I have a simple program that prints out the ASCII table. And I'm printing out the whole thing here. You can actually have it print out just a subset. But the first 32, well, the first 31 are like these control characters, like vertical tab. And there's just really no way to print those. You could memorize them if you want. I had a CS professor who, for some reason, didn't memorize the ASCII table. Anyway, so space 32 is the space. After 30, starting at 33 up to 126 are other printable characters, and then at 127 we have the delete key. So what we see is that it starts off on these low quality, these low, the lowest one that we can print is 33. So when you start seeing punctuation, Like if you see an exclamation point, that's one of the lowest scores that you can get. And so it's not until we hit 65 that we get a character, so A. So when you're looking at quality scores that have A's and letters from the alphabet, those are relatively high scores. So that's why you see here this sequence starts with relatively high scores, and then by the end it's dropping into the numbers. And if you look at the table again, the numbers are lower than the letters. So there are different kinds of scoring mechanisms here. There's Fred 33 and Fred something else. They're generally pretty standard. You may have to look into altering the base for this, but generally it's the score is represented by using one of these characters, and you see that there's a difference in the ordinal value of these, that the letters are a higher ordinal value than the punctuation and the numbers. So that is a rough idea of why those characters were chosen and what they mean. It has to do with their ordinal value in the ASCII table. So with that, if you understand that a FASTQ record has to be exactly 4 lines long, then you can use this extra argument to grep, if your version of grep has this, called after context. So if I was looking for LSU in this FASTQ file, and I said, after you find the line, I want you to add 4 lines. I want there to be a context of 4 lines for each one of these hits. Then I want you to return the 4 lines from the output file. And so let's look at what that looks like. And what we see here is that we've actually been able to grab exactly a whole one whole FASTQ record. And if we get rid of the head, FASTQ, if we look at that, then we see that we've actually found 2 records, and you see here there's a dash here, dash in between to show the difference between the records. So we're almost like we'd have to grep out these 2 lines here, these 2 dashes here. The problem is we're looking for LSU, which is probably not going to occur in the sequence line or in the quality line, but it could. If we were, if we happen to be searching for over amino acids, which we probably wouldn't have a FASTQ file for that, but it is, you could conceive of a string that you're looking for that might occur somewhere else in the record, and there's no way to tell grep. We're only wanting to look in the header. We never want to look, for instance, in the quality line. So to get started, let's, as we so often do, I'm going to copy solution to the FASTX grep, which I've already been playing around with this. And if we just take a second to understand how grep works on my computer here, it wants really 2 positional arguments, which is a pattern and then some number of files. And because it can only search for 1 pattern, but it can do it over multiple files. The pattern comes first, and then the file names come second. And so I want my program to kind of mirror the way grep works. And so if we run this, you're going to see a few more arguments than we've been using for our other programs, for the Roslyn programs. But you'll notice here it requires a pattern, and it requires a file followed by some 1 or more files here. And we have several options here. One is which to tell, we can direct it what the input format is of the file. But the fun thing is we can actually guess at that. So we're going to make this an option. You notice here the default is nothing. I kind of don't like the way that it shows nothing for the default, but it does. And then so for the output format, we can also indicate that. The default, again, is just going to be whatever the input is, and I'll show you a small problem with the way that I wrote this. But it works well enough for the moment. And then we can specify an output file. This is definitely ugly. By default, it's going to go to standard out. but we don't have to indicate the output file. And finally, there is an option to do case insensitive searching, which also has a default of false. So the only thing we have to give here is a pattern and a file. So always trying to make it easy for our users to execute our program and get something out. The input file formats are only going to accept FASTA and FASTQ, and we've used argparse choices for that before. The output, excuse me, the output file format is going to be FASTA, FASTQ, or the FASTA2 line, which I talked a little bit about. It saves a little bit of space in the output. The default is FASTA, where it breaks up the log lines and adds new lines, which is fine for looking at them. It's not like we sit there and really read FASTA files a lot. Really, it saves quite a bit of space if we get rid of those new lines. So I tend to prefer a FASTA2 line. And so how do we write this program? So let's start from scratch and talk about this. I'm going to do a new PY. I'm going to force, and the purpose of this program is FASTX grep, and it's going to be called FASTX grep. And let's look at this, how we would do this. I am going to make my life a little easier here. I'm going to go to the solution and grab a few things here. We do need the list. I'm going to grab whoops. Sorry about that. I'm going to grab my args definition. Definitely have a little problem typing this morning. So the way to represent this, and I'm generally putting these in the same order as my argument definition, just the way I kind of think about it. I want my pattern to be up here, and then the list of input files. These are going to be open file handles. And let me just make a note about this. It's not a terrible thing that argparse file type has been deprecated. I have written a couple of times programs that accept a list of input file handles like this, and it wasn't until I ran into the problem where when I gave it, say, several thousand input files, that I ran out of open file handles. And honestly, I didn't know that was something I could do, that you could open too many files on a file system. So this, because of the way it does a nice job validating the input files and trying to open them and creating nice error messages. But if you have many files to process, you can actually run into using too many system resources. So maybe it's probably a good thing. You could just represent this as a list of strings as file handles, and then handle the bad files as you encounter them. We're going to have input and output format. Those are both going to be strings. The output file is going to be a text IO. I'm going to again use the file type for that. And finally, there will be an insensitive for case insensitive searching. So it is quite a bit to to type, and I give you the how to define do the get args in the book. So I'm just going to go over here and grab my get args here, so that I don't have to go through all of that. And then we can get started much more easily. We can talk about this for a second. There's really nothing here that you haven't seen before. The important thing is that there's a positional argument for pattern. There is a second positional argument that takes one or more. I'm using the plus sign for that. We've seen that before. I'm using the file type here. Again, I will later show you how to get around file type and just use exceptions. I don't like them. I'm using choices here to constrain the input file format to either FASTA or FASTQ. I'm using choices to constrain the output file format to FASTA, FASTQ, and FASTA2 line. And the output file is going to default to sys.standardout. Quite nice. We've used this before. And it's going to open a writable text file if this is given, and so we'll always overwrite that. And finally, there will be a case insensitive sorting by using a Boolean flag for case insensitive, and it's going to return the file, the argparse, the args. So now that I have defined my arguments, always fine to just start off by just printing them. Print args. And let's validate that we have something that works. I'll run it with -H, and hopefully we will see something that looks like the book. And it is unhappy because I haven't imported sys, so always good to go through and make sure you haven't introduced too many errors. Try that one more time. All right, so we have something that looks like the book. These look like some reasonable arguments. Let's just go ahead and run it without -H, and we should, I have to give pattern and file, so let's just say LSU on the test inputs, and which one are you? Yeah, the LSU FQ. And that'll be fine. And it's pretty ugly to look at that, but we are getting something reasonable in all of the slots there. So let's talk about how now we will go about solving our problem. So if you think about all the different ways that you want this to work, what I want is, if I'm looking for the string LSU in this file, I should get 2 records, and they're 4 lines each. So if I run that, I should get 8 lines of output from this. If, however, I'm searching for the lowercase LSU, I should get nothing out of that because it doesn't match it. So therefore, if I run it with the -I flag on the lowercase LSU, I should again get 8 records back. And finally, if I specify a -O and I want it to go into an output file, I should see no output from the program, but now I should have an output file called out.fq, and it should have 8 lines of text in it. And they should be in FASTQ format. So therefore, if I take that previous line and run this with the -O, capital O, with the FASTA format, then you'll see that the format has been changed from FASTQ to FASTA format. So which means essentially it has substituted a greater than sign instead of the @ sign for the sequence header, and it has gotten rid of the 3rd and 4th lines of the record. So it's only outputting the sequence line. So we can also output the FASTA2 line, and you will see here, if you run seek magique from the previous chapter on your output file, you should see this as the output. So here is how you could get started, and I would challenge you to just go ahead and stop the video and see how far you can make it on your own, and then come back and see how I did it. I'm going to go ahead and tell you, maybe you need a little help on the part that guesses the file format. So let's talk about that next. If we look at the out FA, in the first, you'll see that I never had to indicate really the input formats of these files. And that's because I'm looking at the file extension and guessing at them. And I will not guess if the user has told me the input format, but they actually could tell me the wrong format. They could accidentally say FASTA and it's a FASTQ file, and then, well, I'm going to be using seek.io parse on this, passing it that as the format. And so if that blows up, then it blows up, and there's really nothing I can do about it. But and the same will be true if the extension on the file is not correct. And I talked about this in a previous chapter. I have definitely seen files that have been mislabeled, and you have to look at the files sometimes to figure out what the format is. But generally speaking, we can pretty much rely on if it's one of these extensions, FASTA, FA, FNA for nucleotides, FAA for amino acids, it's probably a FASTA format. FASTQ, really the only 2 extensions I've ever seen are FQ and FASTQ. So given that information, we can write a function called guessFormat. And for testing that, I have a bunch of examples for each one of those for the FASTA formats, FA, FNA, FAA, FASTA. I expect when I run guessFormat on these that it's going to return FASTA. It's going to return FASTQ for these 2. And I decided that when it can't guess the format, it's just going to return an empty string. You could have it throw an exception, and that's reasonable if you want to write your code that way. So I would challenge you to. I'm going to go over here and I'm going to create this def guessFormat function that I will be using, and I'll just pop it in here after def main. And I like my little dividers. And for the moment, it's just going to return the empty string. And then I'm going to go over to the solution, and I'm going to find the def guess format. Avert your eyes. Don't look at the solution there. And I challenge you to stop the video and write this function. Just take it one piece at a time, and write the function that will write the meat here that will pass this. And so if we look at PyTest and we run PyTest on the FASTX grep, it's going to right now find the test guess format, execute it, and find that it's not that. So if we were to only put in here just return FASTA, we're going to pass part of the test, but the test is still going to fail because it's not passing FASTQ. So I challenge you, write that function. I am assuming that you have paused the video and written that function, so I'm going to keep going ahead. As far as the rest of the program, I've given you a bit of like pseudocode sort of here to think about. In main, you're going to need to get the program arguments. We've already done that. We're going to iterate over each of the input files. You can use a for loop for that. You should know how to do that well. The first thing that we need to do is either guess the input format, or just assume that we have the input format from the args. If we need to guess the format and we're unable to guess it, then we need to stop. And I'm going to leave it to you to determine how to stop your program. You can throw an exception, and that will stop your program. And I don't recommend, if you're going to throw it, just throw it. And to me, I'm not sure in a program this small, a little utility, I would probably just let the exception go uncaught and let the program fall over. We need to figure out the output format, either from the arguments, or we're just going to use the input format of the file. And I'm going to show you a little bug here that's kind of waiting. And then for each one of the records in the input file, so how are you going to parse that? I recommend seek.io parse. And if the sequence ID or the description matches the pattern that we're looking for, and you need to be able to handle that both case insensitive and not, then I want you to write the sequence to the output file in the correct output format. So this is, it's a little bit complicated, but this is, I think, a reasonable real world program that you will probably be rewriting in your career. So I give you, I challenge you to do that here. I show here how some examples of how you can go about running it and the output that you might expect, and I do think that this is a little bit more complicated than what we've seen so far, and I challenge you to just spend some time trying to write it on your own and then come back. All right, so I will talk about the way I wrote this, and hopefully you came up with something just as cool or cooler, and you did it on your own, and that's great. So the first thing I will say is I do consider myself to be a lazy programmer, and I came about that idea from reading the Programming Perl book out many years ago. I was a Perl programmer for a long time, where they say the three great virtues of a programmer are laziness, impatience, and hubris. And so if you haven't encountered that, the idea here is that laziness is that I just don't want to type anything more than possible. So when I'm writing a program, I want to make the program do as much work for me, and so that I as the user can be lazy. The impatience and hubris, well, you can go look up what those mean. So the key part here is that if I go write a little function here to guess the format, it will save me a lot of time typing on the command line. And so how did I go about writing that? Well, the first thing I wanted to do is split off the extension. We've seen before ospath.split extension on a file name will give me the left-hand side. And so and if we take some of our examples here, and let's just go into a REPL, it's always good to look at that. If I import OS and I say os.path.splitExt, and I use, for instance, this example, remembering that it's going to split it into the left-hand side and the right-hand side. And the left-hand side is going to be everything up to the extension, and then it's going to give me the extension, and that's going to start with the dot. And if you had, I just want to point out, if I had this with like a gzip file, then it's going to give me always the last extension. So in the case where you're working with zipped files, you may need to first unzip them, or you may need to do a little detection to kind of keep backing up and splitting off. If we do os path.split extension on that, then well, that's not going to work. Because it wants yeah, we have to do 0, right? So it would then keep splitting it. That would be how we could do that. So a little side note there. So we are just trying to get the extension off this. Let's do it without the GZ, and then we want to use that information. I only need the extension. So you've seen me before using ospath.basename to just get the base name, but I don't need anything other than the extension. So with that, a couple things I could do is I could just ask for the extension, which is the second part of the tuple that's returned, or I could assign this to root. Well, actually, I don't need the first part, and I can just call the extension, call it extension. So I can unpack this into a tuple where, since I don't need the root of it, I can just assign that to the underscore, and now I have extension is .fa. So several different ways I could go about doing this, and that's what's going on here. You've already seen that trick several times. Now, the next thing I'm doing is I want to get rid of the dot. I don't really need to, but because I could have included it here in my regular expression search. But we haven't really used RE sub, so it's a good opportunity to talk about what this is. So if I import RE for the regular expression, if I do help on re.sub, it will tell me that it will substitute, given a pattern, what I want to replace it with in a string. And there are a couple of extra flags here. So I can use sub. Let's try that. And I will use this version. I only want that. And if I say re.sub and I want to replace the dot, oddly enough, this is going to work. Let's remind myself the pattern that I'm looking for and the pattern that I want what I want to replace it with. Oddly enough, let me just double check that. Like I said, it doesn't work. Let me use this real quick. The regular expression that I'm using is something is at a literal dot at the beginning of the line. So to do that, I say a literal dot and in character class, and I place it at the beginning by anchoring it with a caret here. So another way I could write that would be to do a backslash escaping it. But this will probably, this will complain because Python is now saying, I don't know how to do this escape sequence. I don't know what that means, so I would need to put an R in front of it. So what this is doing is it's using a pattern here where I need to anchor it with the caret sign to say that this starts at the beginning of the string, and I need some way to say it's a literal dot. And one way I can do that is putting it into a character class with these square brackets, or another way I can do it is to backslash escape it, but then it needs to be a raw string so that Python doesn't get unhappy about that. So if I run this line, what I'm doing is splitting the extension, substituting that at the beginning for the empty string, and now I will have, I need to specify file name. So let's say file name is going to be equal to this guy. So file name is equal to that. Whoops. Try one more time. File name is going to be equal to that. And then I'm going to do is an extension of that. And if we look at extension, it's now going to be FA. Let's go back and assign file name equal to FQ. And we'll verify that this seems to work. And then we'll look at extension. Now it's FQ. So this seems to work. Great. Now we have just the extension without the leading dot. And so I have this, I'm using another regular expression to determine if it matches one of the FASTA patterns or if it matches the FASTQ. So the one for FASTQ is a little easier to understand. So let's just look at this expression here. If it matches, and I'm using RE match because that's going to start at the beginning of the string, I don't have to anchor it. So if starting at the beginning of the string, we see an F, followed by, now we haven't seen this before, this is an option. It's a way of grouping. So it's a grouping of letters, the letters AST. So they need to be AST in this order, and they need to be lowercase, just the way I've written. And I could, if I was just trying to capture that group, that's what the parentheses were for. But they the parentheses get overloaded here because I'm also putting a question mark after them. So that says this group of letters is optional. It will additionally also be captured because that's what the parentheses do. That by creating these groups, we're trying to capture them. There is a way for me to say I don't intend to capture them, but I didn't add that here because I feel like that would be putting too much syntax in. So an F possibly followed by AST, but then it has to be followed by Q, and the $ here anchors this to the end of the string. So match is already going to start at the beginning of the string, and this says that it has to end with the Q, and there can't be any other characters after it. Without this $, it could be FQX, and that would match because it would have matched the F and then the Q and then stopped and said, okay, that was a success. But by adding the $, we say the Q has to be the final letter. So let's take this pattern real quick, and we'll say, so we have our extension is FQ, and we can say re.match on a pattern that we have, and we'll say on extension, and it's true, that matched something. Let's change extension to be FA and look at the match, and you'll see it returns. It doesn't look like it returns anything. If we look at the type of that, hopefully you remember it returns the none type. So that is a regular expression that matches the two patterns for FASTQ files. So the other pattern is slightly more complicated. You see it starts with an F. You see that we have this grouping, but now you see that inside the grouping we have these alternations. So it can either be AST, and the pipe here means or it could just be an A, or it could just be an N. That whole grouping is itself optional, which is what the question mark here says, and then it's followed by an A, and then we hit the end of the string with the $. So let's look at this option. So this is going to be true for FA, but if we change extension B back to the FASTQ, we'll see that it does not match. So these are two regular expressions, and you could have these are two regular expressions that will match either FASTA or FASTQ. You could have written a decision tree like an if-else and just gone through that. If it's equal to FA, then return FASTA if it's equal. So, you could have done all of that, or you could have done alternations like, if extension equals FA or extension equals FASTA, and you could write all of that out and then return FASTA. But that's really, that's a lot of typing. And so if you learn how to use regular expressions, then you can have a much tighter program here. So with that, let's get out. I can jump out of the REPL. I can run PyTest now on my FASTX grep. It's going to find my program here. I still haven't actually put that code in, so I'm still failing. Let's just grab this real quick. I'll have to format it. Okay, and let's try that again. And it is unhappy because I haven't brought in the RE, so I will go up here and import that. And that's why, again, I would stress what we're trying to do here is to add one thing at a time and then test our program. And we're still not happy because we need to import OS. And with that, we are now passing the guest format. So now I have one piece of the puzzle done. There's a little more explanation. I have all of that. A little explanation about the patterns. I have some finite state machine diagrams to kind of illustrate that. And then also for the FASTQ. So a literal F, all of this is optional, a literal Q, and then the end of the string. So with that, now I can put all this together and And here I just kind of give you the answer. And so let's go through this one line at a time. So the first thing I'm going to do is I'm going to compile a regular expression with this pattern. So this is something we haven't done before, is taking input from the user, and we're now assuming that the user could give us something quite a bit more complicated than just a simple string like LSU. They can actually give us a regular expression pattern, and we can compile that using the RE compile module. And I'm showing here that I'm using this flag from the RE module called ignore case, and I'm going to use that flag if the args insensitive argument is true. Otherwise, I'm going to use 0. And so I'm going to explain this in detail here in just a moment. I'm going to iterate over each one of the file handles in args.files. Because we're using the argparse file type, these will be open file handles, and I'm using FH to remind myself that this is a file handle. I am going to then assign the input format that's going to be either what was given in the args input format, and if the user provides nothing, then that will evaluate to something falsy, and then I'm using the OR here. So Python is going to use this if it's true, and if this evaluates to something falsy, then it's going to go over here and execute guess format on the name of the input file. And now we've already understood how guess format works, and that is going to return the empty string when it is unable to guess the format. And that is what's going on here if I do not have an input format because the user either didn't give me one or I was unable to guess it. I'm going to use sysexit. I don't believe I've used that here before. I use it quite a bit, and this is a way of stopping my program right here in its tracks. It won't go any farther. So in a way, it's like throwing an exception, except the exception will create this traceback and show me how I got to this point in my program. And I don't like to let my users see exceptions because a lot of times they're not programmers, and they will get this big block of this traceback, which is intimidating for a non-programmer. And they might think they've actually done something wrong, which I guess technically they have, but I feel like it's kind of angry to give them a traceback. Sysexit will simply exit the program, and it works a couple different ways. One is that if you provide it if you don't provide it any arguments and you just call sysexit, it will exit the program with a value of 0, meaning that it exited normally. If you give it a non-zero value, then it will exit with a non-zero value, and then that will indicate to the operating system that it did not finish normally. If you call sysexit with a string, that string will be assumed to be an error message. So it will print the error message, and then it will by default exit with a non-zero exit value to indicate that the program had a problem. So a very handy, quick way of just killing the program with a decent error message, no traceback, and it reports that it's an error, as it should. I don't necessarily like stopping in the middle of this loop, but sometimes you just kind of have to, and I think it's fine for a utility program. So if you haven't used sysexit before, it's a really good function to know about. For the output format, I'm either going to use what the user has given me, or I'm just going to use the input format. And again, this creates a subtle little problem, which I will point out in a minute. Now I'm going to parse that file using the input format that was either guessed or given by the user. And I have this line: if using this regular expression, which I call regex, if I map these items from the record, the ID and the description, and I map those into the function that searches, and the search is already built with either case-insensitive searching or not, if it's true that any of these parts of the record match this regular expression, then I want to write it out. And we haven't seen seek.io write yet. We're going to write the record to the output file in the output. So there's a lot to explain here, so let's go through this one bit by bit. One place to start is just with this any function. And so let's pull up a REPL real quick, and we can do help on any, and it will tell you that it will return true if the Boolean of any of the values in there is true for any of the so it will, given some iterable, it will go through and find if any of them are true. So if we say any of true or false, it is true that one of those is true. And so it doesn't matter where in the order. If I put false first, it doesn't matter. As soon as it finds something that's true, it's going to return true. And so, remembering that 1, 0, and 1, those will act like true. So in the help there, it said basically by calling bool on any of the values there, it will return true if any of them are truthy. And so the same goes for, if I put 2 empty strings here, it's not true that one of those is true, but a non-empty string, even if it's just a space, comes out to something like true. So you need to use this carefully. If you don't actually, if you're looking for actual true and false, then you should probably do something more than just implicitly coercing these to Boolean values. But that's what's going on here. If anything is true, it's going to return true. All works a little differently. All the values, as you can imagine, have to be true. And so if we were to change one of these to false, then that would no longer be true. If we were to change this to something like 0, it also is false, or the empty string, it's also false. So you can mix actual, they're not even actual Booleans, right? But you can mix Booleans and numbers and strings all in this list, and it doesn't blow up, which is actually something I don't like, but that's the way Python works. So all and any kind of go together, and so I use that to determine, to help me to quickly look over both the record's ID and description fields, and that is also using this ignore case that's already built in when I compile it to get around case matching. And in order to explain this, I'm going to have to talk a bit about what are called bitwise operators and this syntax that we haven't seen yet, which is the pipe, which is a way of doing bitwise OR combinations. So let's talk about this real quick. So when you compile a regular expression, you can have these additional search flags, for instance, for case-sensitive matching. And I point out the reason why this is important is that if you are looking for the string LSU that is in lowercase, but the text that you're matching has it in uppercase, you're not going to find it because regular expressions are case sensitive by default. So one way to get around this is just to force both the string that you're looking for to uppercase and the string that you're searching over to uppercase, and now you find it. That's fine, or you could do lowercase. It doesn't matter, obviously. But another way to do this is to provide this additional flag, and I'll just import RE real quick. I don't think I've done this in this session. And if I run this, because I've imported RE, I have access to the RE search function. I also have access to this flag called RE ignore case. And so if I'm searching for a lowercase string, but the string that I'm searching for it's in uppercase, then it will be found because of this flag. And so that can also be shortened to just REI. All of the flags have single letter abbreviation shorthands for writing a little bit tighter code. And so I need a way of compiling the regular expression so that it either has this flag or it doesn't. And so I could have done that with like an if statement, and if this is true, then compile it with this case. Else, I assign this to really just this part. I just compile the pattern without the flag. And I didn't like that. I wanted to come up with a way of having this in one line of code. And so it caused me to really look into what is this RE ignore case. I had seen it before for years, and I decided to to really dig into it. And it turns out it is actually a number, and it's represented in bits. And so I have here the other flags here. If you do help on RE and you search through this, you can find the place where RE ignore case. And let me just show you real quick. If I say help on RE, so I have all of this and I want to find where's this ignore case. I'm going to do / and then start typing, ignore case. And that's how I found this part of the documentation. And that's what I'm including here in the book. And so I see here that these are the short names: A for ASCII, I for ignore case, L for locale, and on and so forth. And so I wanted to understand more about what this is. And so I said, okay, well, tell me what is the type of this flag. And it says, okay, it's a regex flag. And I'm like, okay, well, what is that? And so I read the documentation and it says here that it's a base class for creating enumerated constants. Enumerations are very important. I use them a lot in Rust especially. And they can be combined using the bitwise operators. Without losing their end flag membership and all of this. I'm like, okay, this was all new to me, and I wanted to understand what that meant. And so I figured out that I could actually add 0 to this. So I was like, oh, this is an int. I want to see what this is. If I just say, what is RE ignore case? It says it's RE ignore case. That's not helpful. So it's like, oh, well, if it's an int, then I should be able to add 0 to it. And it tells me it's 2. And I'm like, oh, that's interesting. Why is it 2? And so I wrote this bit of code to go through each one of the flags, and I'm just using the short versions here. And I decided I want to print the flag, and then I want to print the flag adding 0. And I'm putting it here. I want it to be 5 characters wide, and then I want to print the flag additionally in a bit format. So that's what this format string, it tells me to represent the characters as bits. And when I ran that, oh, interesting, when I used this for the book, it actually printed out the flag names. In this version of Python, it's printing out the actual numerical value here. Anyway, what we see here is that the flag is actually 2, 4, 6, 8. You see these are powers of 2. And if you look at this, the ones are marching across the screen. So each one of these bits has its flag in a different place. And so what that means is that they can be combined using a bitwise operator, and they won't overwrite each other. And to show you that, let's represent 1. 1 is actually where the first bit is on. That's why this is 2. And I can represent 2 using this format string. It's not a format string. So this is a way of telling Python, I want this to be a literal byte of 1 and 2. And if I look at 1, it just shows me 1, the normal, and 2, the normal. And the funny thing is, I can combine these two with an OR operation. So for each of these positions, it'll say 1 or 0. And in an OR, if I say true or false, it's going to take whichever one is true. So if I say false or true, it's going to find true. The OR is if you look at your truth table for OR, true or true is true. True or false is true because there's a true in there. False or true is true, but false or false, well, that's false because there's not a true anywhere in there. So it is if we try to do this with the pipes, it basically, with this bitwise operation, it's essentially the same. 1 or 0, well, that's a 1. If we combine these in this position here, 0 or 1, well, that if you OR those together, it's going to be a 1. But when you combine this position here, 0 or 0, well, that's 0. There's not a 1 anywhere in there. So if we bitwise combine 1 or 2, we actually get 3. And that's because the bit representation of 3 is actually the 1 is on and the 2 is on. And that's how in a binary format 3 is represented. So knowing that, this is how the bits get combined. So the 1 bit gets turned on, the 2 bit gets turned on, and because 1 and 2 are turned on, therefore this is the bit representation of 3. And so we have, we can also do AND operations. So the pipe, the single pipe, is a bitwise OR operation. The complement to that is the bitwise AND operation, and that is represented using the single ampersand. In some languages, you will see the single ampersand is bitwise and the double ampersand is a logical AND. And Python uses the actual word AND for logical, and the word OR for logical operations, and the pipe and the ampersand. So knowing that, if I were to AND 1 or 2 together, I actually get 0. Because if we AND 1 and 0, it's not true that both of them are true. And it's not true that both of these are true. So by having, that's essentially, it's also called like masking. So only places where they're exactly the same will those bits survive in the ANDing operation. And so it is a way of like knocking out bits if you want. So what I show here is that if you understand that ignore case is 2 and locale is 4, you can actually, if you combine those together, then you get 6, because you've now turned on the 4-bit and the 2-bit, and those combined is 6. So if you, and I show here kind of the same thing, is it true if I OR these two that is equal to 6? That's true. So that's what's going on when you want to combine these flags. So this is the way that you're able to indicate one or more flags that you want to compile these with. And you do that by ORing them together. So if you didn't know about that, now you do. And this is what I was saying here earlier, that I could start off by assigning this to none, and then if it's true that this is insensitive, compile it with the flag on, otherwise compile it without the flag. And I just didn't like that. I thought it looked kind of gross. I especially don't like mutating a value inside of this. I would prefer to do it even with a if expression. But even then, with an if expression, I'd still have to write recompile pattern twice, and I don't like that. So I came up with this. I think it's a rather clever way of writing this. So therefore, the way to indicate that there are no flags is just to pass 0, and that works. So if it's insensitive, I want to use ignore case, otherwise just use 0. And now you know that those flags are actually just numbers, and the numbers are represented as bits, powers of 2, and therefore, if you were to, for instance, combine all of those together and add them up, they add up to 382, which is maybe counterintuitive, but now hopefully you understand exactly why they do. So this would be a way of combining the flags. You could say ignore case bitwise combined with locale, and therefore that would be you would get both of those turned on. So I have a note here about reducing Boolean values. We've talked a lot about this. This is that truth table shown to you using the logical OR, which has its equivalent in the bitwise OR. And this is and I explained here any basically using that same truth table, true and true, true and false, and all of that. And that is essentially the same as putting and in between those values. You're getting the same. This any true is basically just saying true and true. When you combine those with and, then you get true. And so these are equivalent here. And the same is basically true of all, is doing an OR operation through them. And so that all feeds into this line of code. Now that we have this compiled regular expression, this is the compiled regular expression. It has on it, and let's go. Let me just go grab that real quick. Say right here. This will be fine. I will have to change the pattern. So instead of saying args.pattern, let's make this LSU, and that'll be fine. And so if I say what is help of regex, it is a pattern, and a pattern now has methods on it like find iter, find all, and match, and all that. And so now I can actually say regex match, LSU, and it finds LSU. And even though I'm searching on an uppercase, because this was compiled with the ignore case, I can find the lowercase version of it. So this is now something that I can call functions on. If we look at this line of code here, what's going on is that each one of rec ID is passed into the search function, and then the description is passed into the search, and that is passed as the argument to search, and search returns either a match object or none. In a Boolean context, a match object is not none, so therefore it's true. And so if it's true that any of these, this search finds something in the ID or the description, then this entire expression evaluates to true, and therefore I should print the record. So let's go back and look at our program a little bit more. And for this now, I'm just going to copy the solution to FASTX grep, and let's go look at how our program works in a little more detail. We've now compiled this regular expression. We're going to iterate through each one of the input files. I'm going to either take the input format that was given to me by the user, or I'm going to guess the format. We've already explained how guess format works. If I do not get something back from guess format, and I don't have any input format given to me, I'm calling sysexit to exit the program, and I'm trying to make a nice error string that includes the file handle's name. I'm going to either use the output format that was given to me by the user, or I'm going to use the input format for the record that I just guessed. And now I'm going to iterate through each one of the records in the input file using the input format that was either guessed or given to me. And if it's true that any of this search using this regular expression, this compiled regular expression, matches the ID or the description, I'm going to call seekIO write, which we haven't seen before, but if you do the help on seekIO write, you'll see that it wants a rec, which is the same thing that is returned from seekIO parse, this record, this sequence object that has inside of it an ID, it has a description, it has the sequence. The sequence itself is this seek object that you can call reverse complement and all that stuff on. So if you pass it a record, it will write that to this output file. And recalling that the output file is by default standard out, which is just a file handle that we can write to. And finally, it needs to know the output format, which is very similar to parse. Given a file handle and the input format, it will parse that into a record. Well, this is just the complement to that. It will write the record to an output file with an output format. All extremely useful, and really just a few lines of code to accomplish a fairly complicated program. And if we run our make test on this, I would assume all of this is going to pass. And there are quite a few, as you see, there are quite a few options here that I'm exercising. I'm searching both uppercase and lowercase, searching them insensitively, and so in the case here, when I'm searching one of these, I'm searching and expecting to find it, but in the other one, I'm expecting not to find it. I'm expecting it to return 0, which is not the same as it failing. It's just that's the behavior I expect. And then I search for both of those in an insensitive fashion. Then I search for searching over FASTQ but outputting FASTA, searching over FASTQ and outputting FASTA 2-line. I'm probably not exercising every single possible combination of all the arguments. It really gets complicated. So you try to come up with what are called orthogonal tests, where you can really just exercise one option and verify that it works all by itself, and then you a lot of times maybe are just kind of assuming that if you've fully tested and validated each individual part, that when you put them together they will work in any combination. So testing can get quite difficult, and you can spend quite a bit of as much or more time writing tests as you do the the code itself. So hopefully that explains that program, and you see how to write a reasonably complicated program. I would encourage you to look over the tests to understand how that works. I have some ideas for going further. Like, for instance, a lot of times the metadata will include these key value pairs, like, organism equals a rhizosativa. And so maybe you would like to be able to pull out those key value pairs and only find records for given set of species that you're looking for, or maybe you want to do some taxonomy search to find things that are in a particular clade. There's all kind of things that you can go with from a program like this. This gives you a really nice structure that hopefully you can come back and copy and use in further programs, because it's very common that you will do some operation over a set of files, and you're trying to extract data from them to create some other subset. This will also, you can expand this to handle other input formats like GenBank, EMBL, and SwissProt. I definitely have given my students examples of like having to parse SwissProt files to find data out of those. So a key review here, key points here is that the FASTQ file format, we talked about how it's really quite an insane format. It pretty much has to be 4 lines long. And there are some really technical reasons for that. It's really in many ways an awful file format, but it's what we have, and so we have to deal with it. And so you should know that a valid FASTQ file, the number of lines always needs to be evenly divisible by 4. And so you can find a record just by splitting it every 4 lines. We talked about regular expressions that when you compile them or use them, that there are these additional flags that help control, for instance, if something is case sensitive. I explained about the use of the pipe for the bitwise OR operation that allows you to combine those integers. Those flags are actually integers. They're powers of 2. We talked about that Boolean values can be reduced using AND or OR operations, which is essentially what's going on with the any and all functions. I explained with the do what I mean idea with like writing the guess format. Like you try to write your programs in a way that just do something intelligently and naturally for your user, and remembering that probably a lot of times that user is going to be you. So just try to make the life of your user easier. And this don't repeat yourself, that was key in why I was trying to get that down to 1 line the way that I compiled this. I didn't want to have to repeat RE compile pattern twice. And so I figured out, it's what led me down this rabbit hole to figuring out what this ignore case really was. And then I was like, oh, that's just an integer. So 0 is basically knocks it out. So that was